Howdy, y'all. It's the Diabolic vtutor. We're going to be covering, or recovering, or I guess going more over the log functions. And hopefully things will have some sort of semblance of order. Alright, well, let's just do a little bit of warm-up first before we get into the main bulk of the problems. It's just going to be, I wouldn't say a marathon, but maybe a half marathon of problems. Alright, so let's just start things off with an expansion type of problem. We're just covering the 4 rules from before. No change of base as indicated in the description. Alright, first problem up. We have log base 2 of 32 times a squared times b cubed all over 9 times c power 5 times d. Alright, and when you're typically when you're given something like this, you're supposed to do some log expansions. We have one term, and then we're going to expand it into multiple terms. Just by quick evaluation, we're going to have term number 1, term number 2, term number 3, 4, 5, and 6, just based off of the number of factors inside this inside the argument. Okay, some people treat this as a numerator-denominator type of situation, but I'm going to attempt to circumvent that. We're just going to go straight up passing everything over to the numerator by changing the exponents' signages and therefore bringing them up so we don't have to deal with parenthetical nonsense. So here we go. We're going to change this to exponent -1, exponent -5, and an exponent -1. Again, sending it across the fraction bar following exponential rules. So we're therefore going to get 32 times a squared times b cubed times, again I moved it to the front, to the numerator, so it becomes a power -1, and then times c power -5 and d power -1. So absurdly long now, but that's okay. Again, we're going to have 6 terms in total, so let's just start, let's drop the base. This is base 2. Alright, so we can expand this one. These are all multiplication. We could therefore expand into using the algorithm. The algorithm is applicable because, again, everything is multiplication. So first term, we're going to get log base 2 of, first factor is just going to be 32. And might as well yank out the other constant as well. So it's going to be plus, and then I'm going to do the second one. You know what? Let's go in order from left to right. So we have a power 2 for the second term. So log base 2 of a power 2. Let's just check mark things off so that we don't get confused by the visual clutter. Third term is going to be b cubed, so we have log base 2 of b cubed. Very straightforward, just plus. Nothing too fancy. This is just warm-up problems. So we're finished with the cube. Then next up we have the 9 power -1, so therefore plus. You could go ahead and speedrun this if you wish. If you wish, you could just take that exponent and slam it down in the front, thereby getting -1 times log base 2 of 9. But I'm just going to go not do that at the moment. Alright, so it's just going to be plus log base 2 of 9 to the power of -1. Thus, we have two factors left to deal with, so 2 more terms for the expansion. We're going to have log base 5 of c to the power of -5. And then lastly, final factor becomes final term for the expansion. So log base, why did I put log base 5? I'm so confused. Whoops, keep the same base. As you're doing expansion, you must maintain base 2, base 2, base 2, base 2, not base 5. Alright. I think I was misled with this 5. Okay, but anyway, last one. Log base 2 of d to the power of -1. So that is the expansion. Now we just need to start slam dunking down those exponents. But bear in mind that we do have 32. That's simply going to be 4 times 8, which is just 2 times 2, times 2 times 2 times 2. So 2 to the power of 5 is the factored form of 32. We can therefore, using exponential rule, we take the exponential slammage, take the 5 and slam it down in the front, thereby getting 5 times log base 2 of left over 2. So again, this 5 here as a coefficient came down from there as an exponent, following one of the rules of logarithms. This one, we're going to do the same thing here, exponential slammage. So 2 times log base 2 of a. Exponential slammage. Nice. And then this one is a little funky. Technically 9 is going to be 3 to the power of 2 to the power of negative 1. And then we have distributive property of exponents. Go ahead and distribute that, getting 3 to the power of negative 2. Then we take the exponential slammage, slam dunk that in front, so it becomes negative 2 times log base 2 of 3. Very good. Take that negative 5, slam dunk it in front. Nothing too strenuous. And then we take this negative 1, slam dunk it in front. Alright, so most of these are looking good. That's good. That is good. That is good. That's good. That's good. This one we can further simplify. We have a log base 2 of 2. Learn to recognize the situation. When you have that situation, when you have log base b, and then the argument of the function of the log function matches the base of the log function, then therefore b to the power of what gives us b? Must be 1. So b to the power of 1 gives the same number. So 2 to the power of what gives you 2? It's 1. So again, 2. 2 to the power of 1 gives us 2. Following log mechanics. So there, whoops. I don't want symmetry. Okay. So again, this whole portion here becomes a 1, and 5 times 1. There's no need to write the times 1, so we'll just leave the whole thing as 5. 5 times 1. And then we're going to take advantage of the technologies and just copy paste the rest of this stuff, because nothing else needs simplification. There you go. That's nice. Alright, take one more survey. Everything looks good. And we're done for the first situation. Just log expansion rules. So again, if you just change these ones all into having negative exponents, you could just circumvent having to deal with parenthetical nonsense, which could potentially lead to improper distribution. So, whatever you feel like, of course. Alright, next problem up, we're going to have some sort of a condensation problem. It's going to be log. 2 times log base 3 of 5 is the first term. Second term is 3 times log base 3 of x squared. That's kind of awkward. And then minus 4 times log base 3 of y. And then we're going to have minus log base 3 of z. And then finally plus or minus log base 2 of 10. Alright. And we're going to try our best to condense this as much as possible. We have 1, 2, 3, 4, 5 terms. So we may end up with 5 factors, but make sure you pay attention to the bases. So we have log base 3 right here. We have log base 3, log base 3, log base 3, and then a very awkward log base 2. Unfortunately, our algorithms only really apply to the first 4, so the last term of the minus log base 2 of 10, we shall leave that alone. Okay, so we're going to do as much as we can. So going off of the previous problem's idea, we're going to condense things from multiple terms into as few terms as possible. Thereby, I mean, not thereby. I mean, we're going to do that by going backwards, essentially. We do have coefficients in the front. So we're going to reverse exponential slammage. So we're going to move those back into exponential form. So going backwards, we're going to take this and put that back up there as an exponent. So we're going to get log base 3 of 5 squared, and then this one goes back up here. So the 3 times the 2, well, the exponent, thereby getting 3 times 2, which is 6. Distributive property of exponent, not adding. And then we're going to have a minus, take the 4, move it back up there. Log base 3 of y power 4. This is, yes, that's an exponent, -1 exponent. So once you take that negative exponent and you put it up front, there's still going to be an operation sign of plus. So it'll be plus log base 3 of z to the power of -1. So again, that's going kind of backwards in a sense. So we get this positive, but make sure. So if you take this, if you go back forwards using the exponential slammage rule, that one gets you back to that original sign. So this is correct. And again, this one, there's not much to do with this, so we shall leave it alone. We don't have change of base option at the moment, so we definitely don't have very much to do with this one. Alright, so let us start to collapse things together. Oh, this negative, I'm being inconsistent, right? We took the 4, we slam dunked it, reverse slam dunked it back up there, but the negative sign is still down there. So we're going to take that negative and move it up to the -4, to the 4 exponent as well. So take this negative, reverse slammage, it's now -4, but signage is now plus. Again, this one we don't care. We're just going to leave it alone. All right. So we have 1 argument, 2, 3, and 4. So let's get those all together with log base 3 using condensation rule. So all that becomes log base 3 of, in parenthetical, so this one times this, times that, times that. So I'm going to start to transform that into a 25. And then we have x power 6, and then we have this one. It's a negative exponent, so we can send it to the bottom of the fraction bar to change it into a positive exponent. So we might as well do that in one twist stroke. I can't speak today. So this one again, we're moving down to the denominator following exponential rules, where if you have y to the power of -4, instead of keeping it in the numerator, you acknowledge the location of the invisible fraction bar, and then you send it across by multiplying y to the power of 4, y to the power of 4 to top and bottom. That's the mechanics. You don't need to write that. So this one times this one gives us y to the power of 0, which anything to the power of 0, except arguably 0, is 1. Multiply straight across. So as you see, this one, send it across, thereby getting this. So we're going to get y to the power of 4 on the bottom here. And then lastly, the z to the power of -1, we will do the exact same thing. So instead of putting the z to the power of -1 in the numerator, we can change sign by sending it across the fraction bar. So z to the power of 1 in the denominator, close parenthetical, and then copy paste the minus log base 2 of 10. And that's pretty much it for the condensation of this problem. I think there's nothing else to do, so I'm good to go. Pretty nice. So let me cross out those problems, lest I accidentally do them again. Alright. Next problem up, we have another condensation problem. We're going to have 4 times log base 2 of 4, and then minus 3 times log base 2 of a, minus x times log base 2 of b. And that's it. So 3 terms, nothing too spectacular. We're going to take the coefficients and move them back upwards as exponents. So I'll do that. This is kind of awkward. It's not a constant. It's some sort of unknown value, maybe a variable, but we're going to move it upwards anyway. So we can condense the log base 2's. This is log base 2. That's log base 2. This is log base 2. So our algorithm of condensation will apply to all 3 terms. So let us get to it. We're going to get log base 2 of 4 to the power of 4. Do I want to bother distributing that? Maybe not. This one we're going to take the entire negative 3 and move it up there, so this one becomes positive. Log base 2 of a to the power of negative 3. Same thing here, we're going to take the entirety. Don't just take the x and put it up there, we're going to take the negative sign as well, so the negative x gets reverse exponential slammage, so this one becomes positive coefficient. So log base 2 of b to the power of negative x. So again, you could always double check to make sure that's correct. So if you go back forwards, exponential slammage, this one becomes negative x. Same is true for this one. That one becomes negative 3. So we're good to go. So now there's just invisible 1 coefficients in each of these, in front of each of those. So therefore, just multiply all 3 arguments together, consolidating it, condensing it into log base 2 function. So we're going to get 4 to the power of 4, which, again, I'm not sure. Oh, wait, it's just 16 times 16. I think that's 256. So that's 4 to the power of 4, I think. Yeah, 16 times 16 is that-ish. Yeah. And then since this has a negative exponent, instead of putting it up here with the 256, we can send it across the fraction bar to change it into a positive exponent again. Same thing with this one. We can change it to b to the power of positive x, as long as we send it across the fraction bar. So final answer, I think we are good to go. Yes. And the next problem up, it's going to be an expansion problem. We have 2 times log base 3 of, and then that's 81 times x to the power of x cubed all over y squared and z to the power of 8. So a little bit of awkwardness. We do have this 2 in the front. We can take this one and put it back up here, thereby distributing it to each of those if you wish, but I'm not going to do it that way. I'm going to leave it outside in the front, but I will acknowledge that it's 2 times log base 3. So I'm going to make that explicit, which means this whole thing is in brackets. So we will have to distribute this 2 to all the individual terms after we've done the expansion. So we're going to have 1, 2, 3, 4 terms, so the 2 will be distributed to all 4 of those, each of those 4 terms. So don't forget about this. Alright, so here we go. This is just going to be 81 times this one. And my suggestion is to always change them into negative exponents, so you can circumvent having to use distributive property or having to fuss over that. But I will change this to 3 to the power of 4. Because, you know, this base 3 matches this base 3. And then this one is times x to the power of 3 times negative exponent. So we see that this is going to be a negative term, and then this is going to be z to the power of negative 8. And that one is going to end up with a negative in front of the term. Okay, close the brackets, because again, we're going to distribute the 2 to each of those 4 terms. Let's do the expansion now. So this one expands into, well, this, you recognize those two, right? So we're going to take the 4 and slam it down in the front, thereby getting the log of 4 times log base 3 of 3. But learn to recognize that one. Log base 3, argument 3. Anytime those match up, the whole thing just becomes times 1. So we're done with the first term from the first factor. Now move on to the next factor. We have x power 3. We're going to just go ahead and take the exponential slammage, put it in the front, positive 3 times log base 3 of x. That's some good progress. There it is. This is negative 2. We're going to slam dunk that down in front to get a negative 2 times log base 3 of what? Base y. Done with that one. And then same process, same procedure for this one. We're going to take that negative 8, slam dunk it in the front, thereby getting negative 8 times log base 3 with base z. Don't forget the 2 in the front. It's outside the brackets. As promised, we're going to have to distribute that 2 to each of those 4 terms. So therefore, 2 times 4 is 8. 2 times 3 is 6. 2 times -2 is -4. This is basic cleanup at this point. 2 times -8 is -16. And we are essentially done. This was very weird, so I'm going to put this little dot. You don't have to, but it looks better. This looks like blog, like a weird blog. This doesn't look like a 6. So I'll put this dot here just to make it explicit. Okay. So that should be it. I don't think there's anything else to do. This is clean 8. This is just a regular x. This is regular y. And this is regular z to the power of 1. So everything is looking pretty nice. Which means we are finished with that particular problem. Okay. And that's pretty much it for the expansion contraction type problems. We're going to be moving on to the main bulk of the situations. Main bulk of the problems, I mean. Alright, here we go. Starting us off, we have log base 7. 49 times 49. Is that a coincidence that 49 is 7 times 7? It is not. But anyway, that's getting ahead of ourselves. So there's the problem. We can consolidate those. Now, it's going to be a waste of time if you actually execute 49 times 49. So rather than do that, I'm just going to acknowledge the invisible ones up at the top, and then we will consolidate those afterwards. But using log rules, this is 7 is a base. We're going to raise it to the power of a and equate it to 49 times 49. So again, base of the log to the power of a gets us the argument. So 7 power of a is the argument, which is 49 times 49. So just add the exponents. There we go. Now this is our true problem. This is base 7. 49 is not coincidentally 7 squared. So that is the 49, but don't forget the squaring on the outside. So double E squared. And then we use the distributive property of exponents. So we're going to get 7 to the power of 4 is equal to 7 to the power of a. So at this point, we have successfully matched the bases, so you drop the base, and then a is equal to positive 4, and then we're done. But make sure you double check the answer. Yeah, it's good. No violations of any sort. And we are good to go for first problem. Nice. I should cross this out. Next problem up, we have b minus... we have b is equal to log base 4 of 8. That's kind of funny. And then plus 5. So solve for b. b is technically already solved for in a way, right? So what can we do in this particular situation? Let us try to get it to exponential form. So to do that, we need to get rid of this term. And what I mean by that is we're trying to force it into this configuration where we have log base b of a is equal to c. So we want to get this into that particular form. So that way, once you get it to this particular form, then we can say, oh, b to the power of c equals a. And it doesn't matter if you have like a c plus a d minus f, for example. You can still exponentiate. So you could take this b to the power of that entire thing would be equal to a. So the work, if this is the problem, if this is what we've reached, then you could take b to the power of those 3. So it becomes b to the power of c plus d minus f. And that's equal to the argument a. That's what we want to do with this one, essentially. Probably. We don't have very many tools at this point, but we can't do it like this. We can't exponentiate. We can't say, oh, it's 4 to the power of b because this is awkward plus 5 right here. So therefore, we just move the plus 5 by subtracting it from both sides, thereby getting b minus 5 is equal to log base 4 of 8. And again, we're just doing that because we can probably exponentiate. We can take this one, raise it to the power of b minus 5. Wait, is that the best idea? You know what? Maybe that's not the best idea. Well, let's just see. Let's just see what it looks like first. Yeah, again, it might not be the best idea after all, now that I'm thinking about it. But, too late. We've already embarked on the path, so it becomes 4 to the power of b minus 5 is equal to the argument, which is 8. Not the best situation, unfortunately. This is base... it's actually okay. This is base 4, which we can get to become base 2. And then this is base 8, which we can get to be base 2 as well. Base 2 to the power of 3. So, I guess it wasn't a bad idea after all. So let us continue with the situation. We've already embarked this far in the path. We might as well finish it, right? So again, base 4 transforms into 2 squared. Base 8 transforms into 2 cubed. We can use distributive property of exponent now. So it becomes 2 to the power of 2b minus 10 is equal to 2 to the power of 3. What do you know? Bases match up, which is our intention. Drop the base. Therefore, 2b minus 10 is equal to 3. I was going to say 13 because I already added that in my head. So we have 2b is equal to 13. Therefore, b is not very pleasant. 13 over 2. Let's make sure the answer is okay. Any violations? Nope. Okay, we're good to go. This should be correct. Good to go. Is there an alt strat to doing this particular problem? Yeah, there are. I'm not sure if they're particularly good though. So 8, we could transform that into something that is contains some sort of well, we could change the 8 into something that has an exponent. What am I trying to say? We could change 8 to something with that results from an exponent of base 4. Yeah, that's what I want to say. We can actually change it to 16 over 2. Yeah. If you really want to. Not the best strat in my opinion. But we can change the 8 into 16 over 2. We just copy paste the plus 5. B is equal to that one. Keeping the base 4 for the log, of course. So again, all we did was we just changed 8 into a quotient of 16 over 2. The reason, because 16 is the result of 4 squared, and then 2 is the result of the square root of 4. Versus just keeping it 8. 8 is not any sort of, what's the word? Like you don't get a clean 4 to the power of something is equal to 8. You don't get a clean number. It has to be a fraction, but let's avoid fractions for now. But if you can see the fraction, even better for you. But that's okay. We're doing it this way. So again, 16 over 2 would be an 8. We can actually expand this using our exponential rule, right? So therefore, we can expand it into log base 4 of 16. And then there's the quotient minus denominator. So log base 4 of 2. And copy paste the plus 5 equals b. Okay, so I'm going to go in upwards instead of downwards. That's okay. That's 1. We ask ourselves 4 to the power of what gives us 16. So we're trying to transform this. 4 to the power of what gives us 16, which is why we chose 16 in the first place. So 4 to the power of 2. So this whole term here must be a 2. Because again, 4 to the power of 2 gives us that 16. So term condenses into 2. And then right here we have 4 to the power of something gives us 2. So 4 to the power of what gives us 2? 4 to the power of 1/2 gives us 2. Don't forget the minus sign between those. Copy paste the plus 5. B equals. Okay, so we have here, this one minus 1/2 is 1/1/2 plus 5 is 6.5. That's a mixed number. If you want to change it to proper, 2 times 6 is 12. 12 plus 1 is 13. So 13 over 2, which is congruent with our first answer. So B equals 13 over 2. We are good to go. But wait, there's more. And then right here, you can actually change this one into a factor of 4. Indeed. So we can change it into log base 4 of what? So if you think about it, 8 is just 2 to the power of 3, right? So let's change that 8 into 2 to the power of 3. Unfortunately, this is base 2. This is base 4. We can actually mess around with this a little bit by changing this into base 4. But to do that, there's some shenanigans going on, right? So here's how you can do this shenanigans. We can raise it to 2 to the power, 2 over 2, I mean, right? Because anything raised to the power of 1 itself, but equivalent fractions, we can change 1 into 2 over 2. The reason why we want to do that is so we can use distributive property. We can distribute it to inside right there. Okay, so check it out. It's fancy smancy technique. Well, not that fancy though. So take the 2, distribute it to the inside, and then we could take that 3 cube, and then we distribute it back to the outside. So we just do the old switcheroo with these two factors right there. So thereby getting that. So again, all we did was you can multiply in any order you wish because we're dealing with a positive 2 argument as a base, so there aren't any weird negative shenanigans to worry about. So therefore, this is a valid swappage move. Swapping those, and then now we get 2 to the power 2, which is 4. Power of 3 halves, so we can do the exponential slammage, take that slam dunk that down in the front, thereby getting 3 halves log base 4 of 4. Again, learn to recognize these ones. That's just equal to 1. Alright, copy paste the plus 5 to both sides. So technically still plus 5. B equals. Times 1, we just ignore that. So cross that out. And then 5, we want to match the denominator, so it becomes 10 over 2. And of course, summoning those, we're going to get 13 over 2, which is in agreement with our other 2 answers. And we're good to go. So, in my opinion, this is the fanciest one. I probably would have done it this way. This way is just as valid, though. Yeah. All equally valid ways. Take your pick. If you like working with the fractions, more power to you. Alright, next problem up. We have log of c plus 5 is equal to log of 3c minus 11. Alright, as a thing, a quick note, invisible numbers, if you don't see any number on the bottom, it's actually invisible 10, and this is invisible 10. Not super important for this problem, but I just wanted to point it out. So you don't have to write those base 10s, but understand that if you see no numbers, there actually is a number, and the number is always going to be invisible 10. If you see log with no numbers. Alright, this is kind of a weird situation. We have log of something and then log of something else. But they're equal to each other. This is actually similar to exponential situations. So let me show you something real quick. If you have x to the power of 3 and then is equal to 1 to the power of 3, since the exponents are the same, then the bases must be equivalent. So x equals 111 kind of situation. So if you have x squared is equal to 10 to the power of 2, for example. This one, there are technically 2 answers, right? But in essence, the bottom portions are the same. So x is equal to 10 But as a side note, x also equals negative 10. But I'm just trying to illustrate a point. So if these two functions, this is a squaring function and this is a squaring function, so you can equate the bottom, but don't forget the negative. This one's the more pertinent example. Since the exponents match up, this is a cubic function. This is a cubic function. So if you undo the function on both sides, then the base equals the base. If you have square root of x is equal to square root of 101, since this is the square root function, which is the same as this square root function, we can undo the square root functions on both sides and thereby get x is equal to 101. So something we haven't really covered yet, if you have sine of x, and that is equal to sine of 4, for example, well, what do you think? Right? This is a sine function of x, and then this is a sine function of 4. We could undo the functions from both sides and get x is equal to 4. Now, technically, there are infinite answers, but there's some sort of domain restriction, right? But let's ignore that for now. I'm just trying to illustrate a point. All right. So all that is just to talk about this thing right here, because we have the same function being applied to both sides. So we have log function here and we have log function there. We can therefore conclude that c plus 5 is equal to this other argument right there. Yes, that's what we can conclude. That's very nice. If you want to be a little bit more formal about it, you can. You can exponentiate both sides. Bear in mind, this is base 10, right? This is log base 10. This is log base 10. So what we can do is we can exponentiate both sides. So to the power of 10 to the power of 10 to the power of this is equal to 10 to the power of that. And then this log is the inverse, which undoes this Ford's function. So this one cancels with that one. So we get the same result, but that is the long cut, and this is just the shortcut. So let us ignore the long cut. All right. So again, what has happened? We just canceled out this log and that log from both sides by exponentiating. Technically, now we have this sort of situation. It becomes simple algebra. We're going to minus c from both sides. So 2c is equal to plus 11 to both sides. So 16. That's nice. C is equal to 8. Nice. Double check the answers though. Make sure you take this and you plug it back into the original situation. So if we take this 8 and we plug it there, we're going to get a positive as the argument, which means that's a valid response. We're going to take this 8, plug it in there. We get 24 minus 11, which is also a positive argument. So that's good. So this answer is good. And we are done with the problem. But let me tell you something real quick. If this had been instead a negative 8, as an example, okay, just I know the numbers don't work out, but let's suppose if you ended up somehow with c is equal to negative 8 and then you back plug it in here, you're going to get negative 3 as a result. And again, from last time, logs cannot take in negative values. It's a domain restriction because nothing to the power something, there's nothing that you can raise to the power of something else, no real numbers, that will get you a negative result. So this is not possible given the operations, given the mechanics of log functions. So again, if we somehow end up with this one and you back plugged it in and it didn't work out, then this is called an extraneous solution and you would not report it. This would be empty solution. But we got positive 8, so we're good to go. All right. Moving on, we have log base 505. Learn to recognize those ones, right? And then we have plus another one. You know what? Let us be efficient. Let us utilize technology. We have the technology. Ooh, that's kind of weird. Okay, there you go. And then there's one more. There you go. And then we have is equal. is equal to log base what? Log base 2 of 8 times d. Alright. So this is probably the one we want to work with, right? We have base 5, we have argument 5. Don't ever forget these ones. Learn to recognize them. It's just going to be 1. This is also just 1, and that's also just 1. That's a quick review of why that is again. So with this one, we have log base 5 of 5 is equal to some number. What is this number, right? So 5 to the power of what number gives us 5? That number must be 1. It's 5 to the power of 1 gives us 5. So this whole thing must be 1. So this whole thing must be 1. Alright, so 1 plus 1 plus 1 is just 3. And 3 is equal to, copy paste the right hand side. So log base 2 of 8 times d. Alright, so same strat as before. We have a log on one side and we have terms on the other side. So 2 to the power of 3 must be equal to 8d. So again, 2 to the power of 3 gives us what? The argument. That's very nice. So that's just going to be 8. Divide both sides by 8, so we get final value. D is equal to 1, but don't get too excited. Make sure you back plug it in to make sure it works out. Positive input, yeah, we're good to go. That is a good answer, and this problem is concluded. Very simple. Next problem up. We have a log base 5 yet again. Now it's going to be a little funkier. We have e minus 3, and that is equal to log base 5 of 10 minus log base 1000. Don't be intimidated. Log base 1000 of 10. That looks really funny. Look at all that space in between, but that's what the problem is. So anytime you have matching bases, just get those together. So we have log base 5, log base 5. We should probably move this over to the other side, and then this is log base 1000. That's okay, because this is just a clean 10. So this one is a constant. We can manipulate it. There aren't any unknowns. So we could probably use some sort of rule to make this look nicer. It just looks funny. So first, let us move this over to the other side by subtracting it. So we're going to get log base 5 of e minus 3, and then we have a minus again, subtracting that from both sides. We get log base 5 of 10 is equal to, this one remains on the right hand side. Okay, so this one, there are some fancy smancy tricks if you wish. Should we do some sort of fancy? Yeah, let's do it. We technically already touched upon it doing one of from the prior problems, so we could change this to actually match this one, right? So this is base 10, this is 1000, and 1000 is just 10 to the power of 3. So we can actually change this to 1 to the power of 3, but to do that, we're going to raise it to the power of 1. Just kidding, it's not 1. That's 3 over 3, so it's still 1. So why 3 over 3? Because 10 to the power of 3 gets 1000. And that's what we're going to do. We're going to take that 3 on top in the numerator and we're going to distribute it to the 10. Thereby getting log base 1000 of 10 to the power of 3. And on the outside, the thing we did not distribute inwards is the 1/3. So there it is. Alright, so that's that portion there. That's what's happening on the right hand side. This one, we have base 5, we have base 5. We moved it here, we moved this one to the left-hand side so that we combine them using the quotient condensation rule, thereby getting log base 5 of. Argument number 1 goes in the numerator. Argument number 2 goes into the denominator. Close parentheses. And we're done with the condensation. Let's move that. Okay. This one looks kind of like a mess, doesn't it? So let us clean it up. So this is going to be 1,000. That's going to be 1,000, and then we're also going to do the exponential slammage, move it to the front, so thereby getting negative 1/3 times log base 1,000 of 1,000. Learn to recognize these ones. Not much to do that, so we're just going to copy paste that one. Easy. So this whole thing, 10, 1,000 to the power of what gives us 1,000? It must be 1. So this whole thing collapses to become 1. We still have a negative 1/3 times 1. But let's not write the times 1 anymore. We shall delete that for visual clarity's sake. And here's what we get. We get this one copy paste yet again. Okay. Now we're just going to do the first rule. We're going to take this one. Base 5 to the power of negative 1/3 should yield this quotient. Alright. So 5 to the power of that gives us 5 to the power of negative 1/3. That should be equal to this junk right there. This actually looks really unpleasant. Why did it end up being like this? Interesting. I hope I didn't mess up anything. Did I? Okay, well, regardless, we could still solve for it. So we can multiply 10 to both sides to clear the fraction because we're trying to solve for e. So multiply 10 to both sides. So e minus 3 is equal to, very awkward, 10 times 5 to the power of negative 1/3. And then we could add 3 to both sides. So e is equal to constant times constant plus constant. So we're done with the problem at this point. It's not the most pleasant looking solution. I don't know what I was thinking, honestly. I wrote this problem years ago. Is there a way to beautify this problem? Well, let me think. Let me go back just a few moments. Why does it look so bad? Oh, I see. Okay, well, I miscopied the problem. Having miscopied this problem, this is the correct way to do it. So this is correct. Everything is correct up to this point. At the end, again, it just doesn't look very nice. So you don't want negative exponents, so let's change it to 10 over 5 to the power of 1/3. And some teachers are concerned with this one because we need to rationalize the denominator. This is going to be a good review of that. So we have 1/3 short, so this is 1/3. It's basically short of a whole. So to make this into a whole, you need to multiply top and bottom by 5 to the power of 2/3. 5 to the power 2/3. Because 1 plus 2 gives us 3 wholes. So 3 over 3, which is equal to 1 whole. So no more fractions. We've rationalized the exponent for the denominator, and this one just looks ugly. Don't forget what this transforms into. The rider goes into the house, so it's going to be 5 squared in the house, and then the radical is going to be cubic root right there. So the horse goes outside, and then the rider goes inside the house. There we have it. Don't forget the plus 3. Okay. That's really, really ugly. So let us delete that and move this over right there. So again, this answer is correct for what's written, but I didn't copy the problem correctly. So I'll show you what it was supposed to be. So this thing right here, it was supposed to have a 3 in the front. So that would have made things a lot easier because you could just take this one and move it up there. So we could have circumvented we wouldn't have had to have done that. So take that 3, move it back up there. It would be just straight up 3 right here. And we would have gotten the 1,000 without the 1/3 in the front. So that we wouldn't have this one. And this would just be -1. So that would have been 5 to the power of -1. That would have been 5 to the power of -1. And that would have been a nice answer, right? So the answer it was supposed to be is e is equal to 10 times 5 to the power of -1 plus 3. Send this across the fraction bar. It becomes positive exponent. So the answer was supposed to be 2 plus 3, which is just 5. It was supposed to be a clean 5. Because again, I forgot the 3 out in front right here. There was supposed to be a 3, but I miscopied it. But this is still a valid answer. It just looks funny. Such is life though, right? Finish with that problem. Next problem up. Let me take a quick drink. Alright, next problem up. What do we have? We have log base 6 of what? 2x squared. Ooh, quadratic appearance. So we have 2x squared minus 14x plus 20 is equal to 2. Okay. Not the nicest looking situation. This looks like a quadratic, right? Don't factorize it. Don't go factor happy now. So again, be wary of falling into blindly following algorithms. So again, don't be too excited. What we can do is we take this 6 and raise it to the power of 2 following rule number 1 of logs. Again, the fact that I'm assigning them numbers, like I'm saying log rule number 1 or log rule number 2, it's meaningless. People have different ordering for the rules, but I'm just saying that to say it. Okay. So base 6 to the power of 2 gives us the argument. So 6 to the power of 2 is equal to what? It's equal to the entire argument, so 2x squared minus 14x plus 20. Alright. This is divisible by 2, divisible by 2, divisible by 2, divisible by 2. So let's split that into 2 times 3 times 6. Let's cancel 2's from both sides. So each of those 3 terms will be divided by 2. This 2 will cancel out with those 3, and then we have a leftover of 3 times 6, which is 18. Alright. So now we have a quadratic, but we need to bring this over to the other side. So subtract 18 from both sides, so we can get it into zero product property form. So this is minus 8. That's nice. Factors of -8 that summate to be -7. That's pretty okay. So we have x minus 8 and then x plus 1. 2 solutions. Solving for zero product property. -1 plus 1 is 0, so x is equal to -1. First answer from here. Second answer candidate. If x is equal to positive 8. Don't forget to check your answers though. Are these valid answers? If we plug in -1 here, it becomes positive. So this whole thing becomes positive, which is a valid situation. So -1 is a good answer. Consider 8 now. If you plug in 8, we get a whopping 64 times 2, which is 128. And then 8 times this one, what is that? 80, 112. So minus 112, yeah, we still have a positive answer. So that whole thing is going to be positive, which means this is also a valid answer. So we have 2 valid answers. And we should be on our way. So this one is good to go. Both answers are good. No extraneous solutions. That's gone now. Alright, moving on. Log base 5 of 8. This is getting more. This is getting longer right here. And then we have equals x times log base 5 of 2. That's good, those two match up. And then lastly, minus log base 5 of 2. Being very inconsistent in how I'm writing things. Alright. So, thankfully, all the logs have base 5, so we could probably consolidate them all together. It seems some consolidations are nicer than others, so here's what I propose. Let's move this one over to the other side, because this is a constant. This is log base 5 of constant, and this is also log base 5 of constant. But this is also constant, I guess, but we have a x here, which we can do exponential slammage, which is why I'm going to keep this one on the right hand side. So let us move this one by adding it to both sides. So we're going to get log base 5 of, I can't write today, log base 5 of 8 plus this one, because we're adding it to both sides, is equal to that one. So again, this one we added it to both sides, so it ends up right there. And this one is plus 0. Okay, log base 5, log base 5. This is addition, so we can multiply the arguments to condense it into a singular term on the left-hand side. So 8 times 2 is 16. Is equal to what? Take this one, exponential slammage. Put it up there. So we get log base 5 of 2 to the power of x. This takes us to a familiar situation for today, right? This is log base 5, this is log base 5. We can cancel out log functions from both sides. And the formal way to do it is technically exponentiate base 5, base 5. Once you acknowledge that, this one is the inverse of that one. So you only get 16, and then this one, same thing here, inverse of that one. So we're left over with 16 equals 2 to the power of x. So I hope you see it. 16 is just 2 to the power of 4. Drop the base. X is therefore equal to 4. Don't get too excited. Make sure you backplug. Yeah, it's okay. So x is equal to 4 is a good answer, and we are done with this problem. Alright, making good progress. Moving on to the next block of problems. It kind of resetted. We're kind of going back to simpler problems, of course, but that's okay. I guess the previous problem wasn't too bad. So we have 2 times log base 5 of x. That is equal to, there's only one term now. You see that? No problems here. There are multiple avenues that we can pursue. We can take this one, reverse exponential slammage. Or you could just divide both sides by 2. So divide by 2, divide by 2. So we're going to get log base 5 of x is equal to, again, divide by 2, divide by 2. Much simpler. 5 to the power of 2 equals x. Again, base becomes base to that exponent. And what do you know? Very straightforward. X is equal to 25. Yep, it's a valid answer. We are good to go for the situation. So that's what the simpler route, if you simply divide both sides by 2. What if we didn't divide both sides by 2, right? Let's go with the alt strat. Let's be fancy smancy about this. Let's take this one and do the reverse of the exponential slammage. Let's put it back up there. So put this one back as an exponent. we are going to get log base 5 of x power 2 is equal to 4. Alright. Now we can take this one, raise it to the power of 4, should be equal to x squared. So what do we get? This one becomes, again, x squared is equal to 5 to the power of 4. And then we could just apply the square root to both sides, but when you transition from even powered exponent to odd powered exponent, you have to put absolute value or plus or minus on the other side. So what's the square root? What's half of 4? It's going to be 2. So technically you need to write like this. So x is equal to plus or minus 25. But not all answers are created equal. If you take this negative 25 and you back plug it in there, we get a negative argument. And log functions cannot take in negative arguments as a whole. So therefore, this is extraneous. We only have one solution. Which, you know, matches with our first situation. So that's nice. We avoided the issue by canceling the 2 from both sides in the beginning. But if you take the 2 and put it back up there, you have to do a plus or minus shenanigans. Right there. And then you have to back plug just to double check your answers. So, extra annoying. Why bother? We're done with that one. Again, the difficulty level kind of resetted. But that's okay. Here's the next problem up. We have log base x of 27 is equal to x. Not much to think about, right? We just have a log function, one term on left hand side and one term on right hand side. So let's just take this one, raise it to the power of x, equate it to 27. So 27 is equal to x to the power of x. This is technically bad form, so I'm going to put the 27 on the right hand side. Kind of pedantic, but that's okay. So this problem is a little gimmicky. This is base x, this is base exponent x. This is only base 27 to the power of 1, but we know we can break up the 27 into 3 times 3 times 3, which is just 3 cubed. And not coincidentally, that matches the exact form. So therefore x is equal to positives of 3. We're good to go. Double check. That's valid base. Okay, we're good to go. Alright. Moving along. We have log of 250. Again, technically invisible 10, which may or may not be pertinent. And that is equal to, oh, this is interesting, square root of x plus 1. Weird. And then lastly, minus log, or minus 2 times log of 2. Again, invisible base 10. Some problem makers try to exploit the fact that the 10 is invisible to mix, because it becomes a little more difficult to simplify certain terms if you don't remember that there's an invisible 10 on the bottom. But I wouldn't do that, right? So we have log base invisible 10, log base invisible 10. We have no logs here, so we have optimal strat is probably to move this log over and consolidate with that log. So let us add that to both sides. So let me be a little more efficient. Let's copy paste this junk. Copy paste. Yes. Again, we're going to be adding this to both sides. So copy paste. We're adding it, so it's plus. Yeah. There you go, efficiency. Yes. Okay. Unfortunately, we cannot combine term number 1 with term number 2 because there's an awkward coefficient, so we gotta send it back to the top, thereby getting a log base invisible 10 of 250 plus log base invisible 10 of 2 to the power of 2, which is just 4. And then copy paste this one. Alright. Now that we successfully matched this one, there's no more awkward coefficient, we can use the condensation rule. So we just need to multiply argument number 1 with argument number 2 because it's plus, which gets us a 1000 log base indivisible 10. I will write it out to make it more visually apparent. Alright, well, so at this point you can attempt to take this one and raise it to the power of this one, but I'm not going to do that. So rather, we ask ourselves, this thing right here, they're all constances, and it's not a coincidence that this is base 10 and these ones have a bunch of 10s inside them, right? So that is actually just going to be 10 to the power of 3. And just copy paste the log function, so it's log base 10. Now we can take the exponential slammage rule, slam it back, which feels like we're undoing our prior work, right? But that's okay, because it leads us to somewhere useful. This is base 10, this is argument 10. Learn to recognize those, that just becomes 1. And copy paste this one. Okay, and then of course we can square both sides because this is fractional exponents. As a review, don't forget, radical notation just looks beautiful. You could transform it into fractional notation. Alright, so we have this sort of situation. Take your pick. We can square both sides, or we can be fancy-smancy about this one. So if you want to be fancy, we want to match half exponent. We currently have 1 exponent. So we change that 1 exponent into 2 over 2. And we just split. So we distribute the 2 to the 3. Now we write parentheticals to make it more obvious what we're doing. So again, we took that 2 we took the 2 numerator for the exponent, and then we distributed to the 3, thereby getting 3 to the power of 2 in parentheses to the power of 1/2. Which will match this one. Since outer function matches outer function, we can therefore conclude arguments of the function must be equivalent. So 9 is equal to x plus 1. So x is equal to 8. And we're good to go probably. Make sure you double check your answer though. Yeah. If you put a pause of 8 in here, yeah, it's clean. It's just going to be 3. And we will be good to go. Alright, but alt strats, right? So this is if we had chosen this path, but there's another pathway you could have gone, or we could have gone right here. So rather than doing the more efficient way, in my opinion, we could just take this base 10 and raise it to the power of this nastiness right there. Which means, again, base 10 to the power of this radical nonsense. So 10 to the power of square root of x plus 1 is equal to what? Argument 1000. This is base 10, this is base 1000. We could transform this one to base 10 to the power of 3. Since this base matches this base, we can equate the exponents. So root x plus 3 is equal to 3. Same answer. We're going to, instead of doing this fancy-smancy 2 over 2 trick, let's just square both sides. So squaring left-hand side, squaring right-hand side. This one isn't super safe because you can potentially validate negative answers, but it'll be okay in this situation. So squaring is inverse of square root, so it undoes each other. Distribute is equal to 9. As you see, we get the exact same answer. Minus 1, minus 1. Same answer as before. You know, it wasn't that bad, actually. It was not a bad route. I thought it would be more inefficient, but technically this is inefficient, but that's okay. So either route works out at that point. Okay, consistent. X is equal to 8. We are good to go. Next problem up. We have log base 3 of a quotient. That's always fun. Log base 3 of quotient, which is, what is that, 2x minus 1? All over 17. And equal to right hand side, which is going to be 2 minus log base what? Probably base 3, yeah, base 3. Of 3x plus 2. Same strats as before. So do a quick survey. This is log base 3, this is log base 3, and this is just a constant 2. So we're going to move this log base 3 to the other side so we can condense those two together since they have matching bases. That's probably the main strat. So let us do that. So let me take this thing, copy paste it. We're doing lazy strats. Again, we're gonna add to both sides. So plus the log base 3 of this thing to both sides, so we'll move it to the other side, thereby making this one into a positive situation. Let's take this one, move it here. Oh, that's bad. Okay. So again, we just added this thing to both sides to get rid of this one, thereby getting this response. We have log base 3 matching log base 3. This is a plus, so we can multiply argument number 1 to argument number 2 to consolidate into one term, log base 3 of this thing times that thing. Should we bother distributing? Let's leave it alone for now. I think we have to distribute it at one point, but let's leave it for now. All over 17. That looks weird. All over 17. So the only thing that's happened, this thing got multiplied to the top. Numerator to numerator. So this one, that one ends up on the top right there, because it's technically over 1. Alright, so here we are. Usual avenue at this point. We have one term with a log and we have a constant, so just take this base 3, raise it to the second power, equate it to the argument. Can I copy paste? Yeah, I can copy paste. Let's be efficient. There you go. And then we're going to raise to the power of 3. So 3 to the power of 2. 3 to the power of 2. Yeah, we have no choice but to distribute that nonsense. Well, I tried to avoid it. First to first, and then middle, middle. So we have 4. This is going to be 4x minus 3x. So it's going to be positive 1x. Negative 2. That's kind of bad. And then we have a 9 right here. Okay. Well, can't use zero product property. We need to multiply 17 to that side and then subtract it from both sides afterwards. So let's do that. 17 times 9 is a rather unpleasant 170. That'll be 10 17s, but we need to take away 1 17. So that's going to be 157. Yes. To again 150. Did I say 157? I mean 153. What am I saying? Okay, that's what we got, and then we're gonna move it over to the other side so we could set it up for zero product property. Oh, it becomes a very clean 160. Yes. Brilliant. Alright, so nothing to factorize, unfortunately. So take your favorite quadratic factoring method. factors of 6. And then factors of 160. It's probably 16 and 10, right? Right? Let me think. 30 and 32. Ooh, no, not quite. Well, we need a little bit more than that. Okay, well, I thought I could get away with that. 16 and 10, 8 and 20. That's probably good enough, right? 24 and 40. Ooh, no. And then we have... Oh, that's kind of awkward. Okay, well, I'm going to downtick this one even more. 4 times 40. One of these should be right. It looks like there should be the intermediate ones, honestly. This is 30 and 32, which gets us very close, but it's not quite right. What do you think about that? We have, oh, missing the 5. 5 times and 4 32. Yeah. Which one is correct? 30 and 32 again. Well, let me think. Factors of 45 times 2 times 2 times 2. 8 times 5 is 40, and then 40 times 4. We already have the 10 here. We already have the 8 there. We already have the 5. What are we missing? I think that's it, right? 8 and 10. Wait, what? 8 and 20, I mean, you know. That's already here. Let me think. It's probably really obvious and I'm just not seeing it. What is missing? Well, let's put this in order. Okay, I guess the next one up is 2 times the rest of this. So it's going to be 80. That's definitely drifting farther from what we want. Just for completion, right? 1, 2, 4, and then 4 times 2 is 8, and then 5 is here. 5 times 2, 8 times 2 is 16, yes. I'm just bad at multiplication today. Let me make sure I didn't miss. Let me double check something. 2x times 2 is 4x. 4x minus 3x is indeed 1x, yes. 17 times 9 is 9153. Yes. Yep. Okay. I don't think any of that is wrong. 3 to the power of 2 is 9. Okay, so it should be correct at this point. It's just my brain's not working for this problem. This is 30, this is 32. That's not correct. So that's 30 and 32. That's funny. Okay, well, let's put an end to these shenanigans. Let's just resort to quadratic equation. So negative b, negative 1 plus or minus the square, oh, I'm sorry. Yeah, negative 1 plus or minus the square root of b squared minus 4ac. So minus minus is plus. 4 times 6 times 160. Ooh, this is really bad. All over 2a, which is 12. Okay, well, what is that nonsense, right? So we have 1 plus... Ooh, that's really bad. That is really, really bad. I really hope I didn't mess up a calculation somewhere. Unfortunately, I will resort to cheating. I'm gonna go on my calculator real quick. Because I'm much too lazy at this point. 1 plus 24 times 160. This is an irrational number. What the heck? Okay, well, that explains things. That explains why this one gets all screwed up. Because there aren't any good factors. Checking this one, we get a very bad number. But let me check one more time. What do we get? Square root of b squared. B is just 1. 1 squared is 1, yeah. Minus 4ac. So plus 24 times 160. Yeah, unfortunately. So the radical part is irrational. Goodness. That's 1 plus or minus 61.975, etc. All over 12. That's really bad. Well, that explains why I couldn't get it right here. Is this just a poorly designed problem, or did I miscopy it? Let me see. Let me see something real quick. Was anything slipped up in translation? No, this is a perfect copy-paste with a sign alteration. And then this one gets multiplied to the top. That's like so. 3 power 2 is 9, yes. 17, yes. Distributing property. 3x times 2x is indeed 6x squared. 4x minus 3x is 1x. That's correct. Ah, okay, well. It just ended up being an improperly designed problem, unfortunately. But it is what it is. That's fine. So let's just cover the main idea. So let's just talk about this real quick. So again, unfortunately, this one, the factors of them are irrational. But let's talk about it. So if we had, let's say we got something like x minus a times x minus b, right? Let's just pretend make-believe, right? So this one, if it successfully factorized into this one, then we would have gotten 2 solution candidates. X would be equal to a, and then x would be equal to b as answer solutions. And then those ones, we need to take them and plug them back into there to make sure you don't get any negative arguments. All right. So we would have gotten 2 answers. And just make sure you plug them in. Make sure you don't break the log base 3 function by having a negative argument, and then it would be good. But unfortunately, we just have this nastiness right here. So one answer will be huge negative, and then the other answer will be some sort of positive. It'll be close to 5. It's like 5-ish for the positive answer. And then the negative answer, will it have worked out? Yeah, if we plugged in the negative answer into here, this one becomes negative as a whole for the argument. So we have to exclude the negative answer, and only the plus 5 one-ish should work out. Yeah, we'll get 5-ish. If you have 10 minus 1, that's positive, so this part will be positive, and then you have 5-ish times 3, so this whole thing will be positive. So we only have one valid solution. This is the valid irrational solution. Again, it's 5-ish, because it's nastiness right here. You're going to get like 60.975 over 12, which is approximately 1/12. 5.1-ish. I'm just going to cheat and call it. And that's the only valid answer that we're going to get. That's it for this particular problem. Unfortunately, it just ended up being a little nasty, but still workable. What a waste of time on the factorization. Okay, moving on. Next problem up. Hopefully, things don't go awry. Wait, is that the problem? Okay, I'm kind of scared that... I'm kind of worried that this problem is copied incorrectly, but let us trudge forward. Let us move forward. Onwards is forwards. So we have quantity 2 times quantity log base 6 of 2 minus, oh, this is weird, log base 10 of 2. So already the logs are mismatched. which means we need to separate them somewhere along the way. And then we have a plus log base 6 of x equals what? Log base 10 of 25 minus log base 6 of 3. Okay. So, same thing, same acknowledgement. We have log base 6, log base 6, log base 6. This is log base 10, log base 10. So we're going to distribute this to each of those and then move this one over to that side, and we'll move the 6 log base 6 with the rest of the log base 6. That's the plan of attack anyway. Nothing too complicated, so let's distribute first. We're going to get log 2 times log base 6 of 2 minus 2 times log base 10 of 2. Copy paste. Let's just cheat and copy paste the rest of this. So we just distributed all we did was we distributed this 2 to those 2 terms, thereby getting this term and that term. We shall move that over to right hand side, and we'll move the log base 6 to the left hand side. So let's copy paste. Whoops. So copy that, paste that. Well, let's get the log base 10 to the right hand side by adding it. So plus to both sides. And we're going to move this over by adding it to both sides. Thank you, technology. Okay. So all the log base 6s are on the left hand side. We cannot combine them all cleanly because there's 2 coefficients in front, so we're going to move it up there, right? So let's take that 2. Shrink that exponential slammage, reversal slammage. Move it up there. Same thing here. We cannot combine log base 10 with this awkward coefficient 2 in front of the log base 10, so we're going to take this one. Reverse exponential slammage that one as well. So take that exponent for the 2 right there. So what do we have at this point? Well, we have a couple of 2 squares, so let's just change this into a 4. 2 squared is 4. This one will also change it to simplify it into a 4. And now things are much easier to combine. So we have 3 terms with log base 6. So all we need to do is multiply the arguments. So 4 times 3 is 12 times x is 12x inside the log base 6. So that's successful condensation for the left-hand terms. And then for the right-hand terms, we're going to have the 25 argument times the 4 argument, base 10. I'm going to write the base 10 just to make things as clear as possible. So 5 times 4 is 100. Is that a coincidence? Alright, let's take this one. And move it over. Don't be shy. What's that? That's just going to be 10 to the power of 2, right? A very familiar face. We're going to take that exponent, slam it down on the front. Feels like we just undid our work, right? Again, I spelled out the 10 here to make it as explicit as possible. But you won't always see the invisible 10 on the bottom. You just see something like this. But this whole thing collapses and becomes just 1. Let's copy paste that. Let's just put ditto marks. Ditto marks. This one I'm going to copy paste. Alright. Very clean at this point. We just have a log term on one side and constant on the right hand side. So 6 to the power of 2 is equal to 36. Divide 12 on both sides. X is therefore equal to 3, and then we are good to go. Yes. Wonderful. Now we have 1/4 log base what? Log base 3 again. Log base 3 of x is equal to twice log base 100 of 10. Alright, so I remember to copy the coefficient this time, so we can reverse exponential slammage to match 100 with 100. So let us just do that right away. So let's move this up there, thereby getting log base 100 of 100. Recognizing this one, this whole thing here just becomes 1. We have a 1/4 here. Let's just copy paste. So we have two. We're at the crossroads. We could take this exponent and slam it back in the top like that, or you could just simply multiply 4 to both sides, which I think is the optimal option. So distribute to this term on the left hand side and distribute the term on the right hand side. Do full distribution. So I'm kind of sloppy in my notation, so I just put parentheses around the entire equation, but this one gets multiplied to here and to there. So 4 times 1/4 is just 1, clearing the coefficient, and 4 times 1 is 4. Nice situation. 3 to the power of 4 equals x. 3 to the power of 4 is just going to be 9 times 9, which is 81. And then we are done. Make sure we double check, of course. 81 plugs in just fine right there. So yeah, we're good to go. Good answer. All right. Next problem up. We have log base 4, 3x minus 16 is equal to constant 4 plus log base 4 of 1 over x. Alright, there we go. Quick evaluation always, always, always. This is log base 4, log base 4. They are separated at birth, and then we have this 4 right here. So we should probably move this over to the left-hand side. So let us do that by subtracting it from both sides. Yeah. I'll just rewrite the whole thing. Not too much to write, so we're moving it over to the other side by subtracting it from both sides. And the 4 is just copy pasted. There we go. Now what do we do? Well, basically this is log base 4, this is log base 4. We should combine the argument number 1 with argument number 2. It is a division though. But we have a trick here. This is basically 4 to the power of negative 1 using the funky exponential rules. We can take that negative 1 exponent and slam dunk it in the front, thereby getting a positive log base 4 of 4. Copy paste the rest of this stuff. Alright, well, maybe we shouldn't have moved it. Wait, something feels wrong here. Oh, why did I put a 1/4? Whoops. Okay. Everything else is correct though, I'm sorry. This is basically 1 over x, not 1 over 4, but the movement is correct. This is what I get for not copy pasting. So that's not a 4, this is not a 4. But all other moves are the same thing. Yep. So this is not a 4. That's just an x. Okay, okay, yeah, everything's correct now. Copy paste the 4. Alright, we're good to go. So we have log base 4, we have log base 4. This is now changed into a positive, so we can just simply multiply the two arguments together. So this argument times that argument, which should get us 3x squared minus 16x. Inside the argument, log base 4 is equal to what? Right hand side is still unchanged 4. Alright. Takes us back to this nice situation now. We just have log single term on one side and then constant on the other side. So take 4 to the power of 4 equals argument. So 4 to the power of 4 is equal to, what is that? I don't know off the top of my head. But let's copy paste this. You know, maybe we could get away with not distributing this nonsense. Let's just subtract it from both sides. And let's hope I didn't botch up this particular problem. So this is 4 to the power of 4 is equal to 0. So we ask ourselves, what are the factors of 4 to the power of 4 in conjunction with the 3 that will produce a negative 16? So let us see. So this is 3 and 1. That's technically a 4 times a 4. Whoops, that looks weird. Right? This is one possible factor combination. We can move the 4 over to here, right? Yeah, let's do that instead. Let's do 4 times 4 and 4 times 4 as a combo. And I feel that that's correct. Right? We have 4 times 4 times 3, and then we have 4 times 4 times 1. So if you subtract those two, we're going to get 2 times 4 times 4. It's not quite 16 though, so we need to play around with the factors a little bit more than that. So let us steal a 2 from here, times 2, and we'll multiply it to there. And wait, what am I saying? Yeah, let's break up this 4. I'm sorry. Yeah, let's break it up. So it becomes 2 times 2, but as a candidate, we're going to take that and just put it right there. Okay. Now we're going to multiply this times this, which gives us 2 of 16s. And that's going to be 32. And then this is 8 times 3, which is 24. Subtracting those two, we get, oh no, we only get 8, which is not quite 16. Well, that's kind of a bummer, right? Okay, let's backtrack just a little bit. 4 times 4, 4 times 4. Why did that not get us the right answer? Okay, well, let me think about this. Two times 16. Yeah, that's not quite right. So if we take the 2 and transfer it to here, that's still not correct, right? That takes us to 24 minus 16, which is going to be 8, not negative 16. So not quite right either. So we need slightly bigger number. Yeah. 2 times 16 was too large. Oh, I hope I didn't screw up the problem yet again. Let me think. Okay. You know what? Let's just jump straight to quadratic equation at this point. So negative b plus or minus square root of 4ac. I'm sorry, square root of b squared minus 4ac. Yeah. Oh, wait a minute. This is 4 to the power of 4. Whoops. Almost screwed that up. Yeah, this is really nasty. I wish I didn't make up such a bad number for there. Okay, so 4 times 4a times c. I already canceled out this negative. 4 to the power of 4. Okay. Well, This is actually a nice scenario. This is just, I should have left this as 16 squared. So 16 squared is just going to be 4 times 4 squared. This is also just a bunch of 4s. So plus 3 times 4 times 4 power of 4. Is there a nice way to add this up? Yeah, I think there's a way to play around with this, right? Well, we can change this into 4 times 4 squared plus, and then let me make it easier on my brain. Let's distribute that one. So it's going to be 4 squared times 4 squared, which is 4 to the power of 4, which matches this one. So we have 1 of those 4 to the power of 4s, and then we have 12 of those 4 to the power of 4s, which means we have 13 of those 4 to the power of 4s. Yeah. That looks irrational, doesn't it? Well, I flubbed it again. So all over 2a, which is 6. Well, that's another rather unfortunate scenario. So this is going to be equal to, let's just do the most we can. So it's going to be 16 plus or minus. We could take the square root of that one. This is going to be 4 to the power of 2. Copy paste the leftover 13. Yeah, that's causing the issue right there. All over 6. So therefore, this is 16. We can divide top and bottom by 2. So we get 4 plus or minus 4 square root of 13 all over 3. So we have two answers. One of which is going to be positive, and then the other of which is going to be negative. So the negative answer is 4 minus 4 root 13 over 3. So this is probably not a good answer. And the other answer will be 4 plus 4 root 13 all over 3. All right. So let's just take a quick step back. Yeah. So you see how this one's going to give us a negative answer? If we plug in a negative answer into here, this whole thing becomes negative, and you can't take the square, you can't take the log of a negative value. It'll be a domain issue, so therefore the negative answer must be excluded. Then the positive answer should work out. All right, so what is the positive answer? I don't know. So 4, this is a really bad number, right? So the closest one is 3. Square root of 9 is going to be 3. So this is bigger than 3, but let's just assume square root of 9 for simplification for the mathematics for the checking. So this is going to be square root of 9, which is 3, and then 3 times 4, which is 12, and then 12 plus 4 is 16 over 3. So this is greater than 5. That's what we want. Greater than 5, right? So we have greater than 5 times 3, which is greater than 15. Greater than 15 minus 16 could be negative. Ooh. But I think it's bigger than that. So I have a little bit of, let's just say this is good enough, right? You know what? I shouldn't. Let us do 4 root 13. 4 times the square root of 13 is 14.4. 14.4 plus 4 is 18.4 divided by 3 is 6.14. So this is approximately 6.14. Yeah, okay, it's good. Because if we have 6.14, which is 18-ish, minus 16 is a positive input, which means it's going to be a valid answer for the situation. So we're good to go. Again, not the most beautiful answer. That's extraneous, but this is a valid answer. Because if we back plug it in, we get a positive argument inside there. So it should be good at this point. I'm a little disappointed though. That answer was supposed to be good. But that's it for that one. I want to check my answer. Hold Of course, VOD watchers could easily skip over this portion. I probably won't timestamp this particular section, but for sake of completion, let me delete this part right here. I think I wrote this problem today, very last minute, and I think that's why I ended up being wrong, or maybe I simply miscopied it. All right, let me quick speed run through this problem. Let me think about this. Let me think. Yeah, so let me, VOD watchers are just going to simply skip this part, but let me just go over this one. Same strat. Move it over, but it'll be a minus minus, so it's plus, so it's times, so it's going to be 3x squared minus 16x is equal to 4. 4 to the power of 4, that's really bad. I think that's where I miscopied it. It's probably supposed to be 64. You know what? Yeah, this is probably supposed to be a 2. Let me change it real quick. Let me see what happens. This is supposed to be a 2, I think, and this is supposed to be a 2. No. It's supposed to be a 3, I think. Yeah, this is supposed to be a 3. Okay, let me change the problem. So once we get 4 to the power of 3, that's 64. I feel this is now right. Okay, so it's supposed to be 64, because 4 to the power of 4 is too big. Okay. I think I've come to the realization. Yeah. I think when I was making the problem, I miswrote this as, I'd miswritten this as 4, because 4, I thought it was 4 times 4, which is 64, but it's 4 to the power of 4. So that is supposed to be 3. Okay, I think it's supposed to be correct now. So minus 64 from both sides. I feel this is correct. Zero. Yeah, factors of 3, 3 and 1, factors of 64, 8 and 8, yep. That gives us 24 minus 8. It's a negative on the 24, therefore it gives us negative 16, and that is what it was supposed to be. Okay, good. Well, shenanigans, right? Alright. So this factorizes basically into 3x and, what was it, x. The 3 gets multiplied to the 8. Oh, they're both 8s. That's easy. And then the larger of the 2 gets the negative sign. That's the larger of the 2. This is the smaller of the 2. Okay, so it's 2 answers. Okay, well, that confirms it. Okay, so for VOD users, or just skip to this particular problem. Okay. So let's pretend none of that ever happened. Let's do this particular problem. Alright, now we have this particular problem right here. This is log base 4, this is log base 4, this is just a constant. So let's get the two log base 4s together by moving this over to the other side. So let us copy paste. And again, we're moving this by subtracting it from both sides, so the sign changes from a positive to a negative. And let's make some room. There we go. Alright, now it's going to be beautiful. Absolutely beautiful. Alright, we're going to have a minus minus. Well, that's kind of awkward, right? But that's okay, because we can change this one into a negative exponent. Right? So this one changes exponential rule into x to the power of negative 1. And then what we can do is we can take that negative coefficient right there and we could reverse exponential slammage it, move it to the top, thereby getting positive log base 4 of x to the power of negative 1 times negative 1, which is going to clear and produce positive 1 exponent. Perfect, which is what we want. We'll copy paste this one. I'm going to rewrite it because it looks ugly. There it is. Copy paste the equals 3. Alright. We have log base 4. We have log base 4. Now we could just simply multiply the two arguments together to condense those two terms into one term. log base 4. So we're going to get 3x squared minus 16x is equal to 3. Now here's where the magic was supposed to have happened. It's 4 to the power of 3 gives us 64. 64. 64 equals what? The argument 3x squared minus 16x. Now, things are what they're supposed to be. We're going to subtract that from both sides. Oh, I need a water check. Hold on. Let's pause for a moment as I drink some lemon tea. Hold on. All right. There we go. 3x squared minus 16x minus 64 is equal to 0. What are those factors of 64 and factors of 3? That can possibly produce a negative 16 in the middle. Factors of negative 64, negative 8, and 8. What do you know? 3 times negative 8 gives us negative 24. 1 times 8 gives us positive 8. If you sum 8, we get negative 16, which is what we want. Perfect. So therefore, we have a 3x multiplied to a negative 8. And a 1x multiplied to a positive 8. So that is the factorized form of the quadratic, and that is equal to 0. We are using zero product property, therefore x is equal to 2 answers. We have a negative 8 over 3, and then we have a positive 8. These are 2 answered candidates, but don't get too excited again. Always double check by back plugging in the values. So let's take that and relocate those real quick to the start of the problem. Always check back at the start of the problem right here. Okay. So we can see that the negative 1 right here is going to cause this to fail because log functions cannot take negative arguments. This cannot be negative as a whole. So therefore this answer is extraneous. So extraneous. The positive 8 works just fine there, and it works fine. 24 minus 16 is a positive value, so we are good to go with the 8. So this is the only correct answer. X is equal to positive 8, and I'm glad this problem went swimmingly. So we're done with that particular problem. Very nice. Nothing, absolutely nothing went wrong with that problem. Alright. Next problem up, we have log base 2. Ooh, this quadratic looking thing. X squared plus 9x plus 81 minus log base 4 of 1 is equal to what? Log base 2 of 1 over x minus 9. This is what we have. Some weird things. This is kind of weird. We have log base 2, which matches log base 2. So you can bet we're going to move that over to the other side. This is very similar to the previous problem. The only difference is we have this funky looking thing right here. But, you know, just ask yourself. You know, let's move it first. Let's move it. Let's move this one to the other side, and let's move this one over to the right-hand side. But this one, I'm going to change it into negative exponent first. So we're going to transform it into log base 2 of x minus 9 to the power of negative 1. Take that exponent and slam it down to the front, thereby getting negative, like that. So again, just exponential rules. We just changed the 1 over x minus 9. We just passed it through the fraction bar to the other side, change it to a positive exponent. But the I'm sorry. Let me say it again. So this basically is just 1 over a, right? Which I don't like that one, so I changed it by setting across the fraction bar, thereby becoming a to the power of negative 1 over 1. And because there was a negative 1 exponent, we took that and slam dunked it down in the front. All right. So that's gone, and it's right here. Which means we could just simply add it over to the other side, and we could take that one and add it over to that side. Yeah. Ditto marks. Okay. So again, we're going to add this over to the other side, and we'll add this over to that side. So let me expedite the process by copy pasting. So copy paste that junk, and we're going to add this over to. We're going to add that to both sides. So again, plus this to both sides, so the sign changes, and then this one gets plus to both sides, so becomes positive on the right hand side. So no magic tricks, just simply algebraic manipulations. This needs to be positive though. Alright. We delete this stray mark. Alright. So this is what we have. So again, just to recap, this one we changed into a negative exponent, but we slam dunked the exponent down in front. Then we added it to both sides, thereby getting positive log base 2 of x minus 9. And then this one, we just added it to the both sides, thereby getting this one. Okay. And we move this one over to the right-hand side, left-hand side, so we can consolidate with this log base 2. So all we need to do, ooh, this looks kind of bad, doesn't it? Well, we're going to have to multiply those two together to consolidate term number 1 with term number 2. Yeah, that's what we have to do. Let me save that for later. Let me just put the work down. Close that, and that's all within brackets inside log base 2. This side, what is that doing, right? Now recall that this whole thing, we could always set it in our head equal to some number n. So 4 to the power of what number n gives us 1? 4 to the power of n gives us what? Well, anything to the power of 0 gets us 1. So therefore, this whole thing is just 0. So n equals 0. Because again, 4 to the power of 0 gives us 1. So this is just a trick. Change it to 0. Alright. So that's incredibly nice, and I think I botched the problem already. Well, it was a good try, right? Because I think, yeah, we're not going to get a nice situation, unfortunately. Let me think about this. Well, I see where things have gone wrong, unfortunately, and too bad. It is unfortunate. We'll carry on as best as we can. Well, I hope you recognize that this is actually a factored form of a difference of 2 cubes, because this one, if you square it, takes you to here. That one, this one times this one, flip the sign, gets you to positive 9x. And then lastly, negative 9 squared gives us positive 81. So this one is actually a difference of 2 cubes. X cubed minus 729. That is that. Alright, so we have log base 2, unfortunately. That's equal to 0. Again, I messed up the problem, but we can still do the problem. So 2 to the power of 0 gets us an awkward 1. This whole thing is x cubed minus 729. So we can still answer the question, but it's kind of awkward. So we'll add it to both sides. X cubed is equal to positive 730. Therefore, x is equal to, you just apply the cubic root to both sides. So cubic root on the left, cubic root on the right. So x is equal to the cubic root of 730. And that should be our answer, but let's double check. So if we plug it in, that should give us a positive answer. Positive answer. So this whole thing, argument, ends up becoming positive if we plug this in, so that's okay. And if we take this and plug it into there, that will also give us a positive argument. So this answer should be good. Again, not a nice looking answer, but it should be technically correct. Yeah. So unfortunately, the problem was poorly designed yet again. I literally wrote it today, so I didn't have enough time to do test runs with the problem. But it's still solvable. It just doesn't look very nice. So I think that should be it for that problem. But let me double check real quick. How could I have made the problem a little nice? No, I don't think I could have salvaged this problem. I think this just needs to be... Wait. Wait a minute. Let me think about this. Was I overthinking it? Maybe I was... Oh, wait, hold on. Something's wrong here. Maybe it is a nice problem. Hold on, let me double check. 2 to the power of 0 is equal to 1. Yeah, that's correct. Yeah, I just think this problem... I just didn't proofread the problem well enough. I didn't test run it. That's okay. Let me just take one more look at the problem. Let me delete this. Again, this answer should be good. It just doesn't look nice. Let me see that real quick. So, again, the idea is this one is supposed to be 0 because 4 to the power of 0 gives us 1, right? So this whole term here just is nonsense. Well, it's not nonsense. We could just cancel it out. And then, can't we just, since this is log base 2, this is log base 2, can't we just simply exponentiate on both sides? So thereby canceling log base 2's. So, wait, what? How come now it's changed? So we have x squared plus 9x plus 81. That's equal to this nonsense, right? Oh, no, it's still the same thing, yeah. Because we have to multiply this to both sides. So multiplying both sides by x minus 9. This one distributes to here, and this distributes to that entirety. Yeah, we're going to get a difference of 2 cubes yet again. So x cubed minus 729 and equals 2. This one doesn't become 0, which is what I wanted it to become. But it just becomes 1 instead. So, okay, same situation. That confirms it. Poorly written problem. If only I had proofread things. That's okay. Again, technically it's still a correct answer. It just doesn't look nice. And hopefully this last problem, final problem tonight, hopefully it's good. So we have log base 3 of x. This one I had also written earlier today. Is equal to 1/2 log base 2 of 256. And that's minus log base 3 of 2x minus 9. There we go. Take a quick survey. This is log base 3. That's log base 3, so they are separated. We need to move this one over to the other side. This is log base 2, but everything is a known value. So we can probably clean this part up. Alright, so let us move one term to the other side. So again, we're going to take this one, add it to both sides, so it'll become plus log base 3 of 2x minus 9. And let's move everything over to make space. Yeah. Oh no, not enough room. Well. I should have just rewritten them. There we go. So yeah, we just move this one over to the other side. Not particularly riveting. Alright. That's what we get. This side can probably be cleaned up, but let us combine log base 3 with this log base 3 term by multiplying argument number 1 to argument number 2. So log base 3 of distribute 2x squared minus 9x. Close parentheticals as equal to, and then this one, what is this nonsense happening right here? We could take this exponent and move it to the top. So take that exponent, exponential slammage, reverse exponential slammage. Wait, let me say that again. This one right here, we're going to move it back up there. So no negatives. And 256, if you memorized it, it's just going to be 16 times 16, which is 16 squared. Not coincidentally, right? So that is what it becomes, and we could distribute this exponent to the inside, thereby getting log base 2 of 16 to the power of 1, which is part of the cleanup. So let's take this one, move it down. That one is right there. Okay, so that's kind of clunky. So we ask ourselves, 2 to the power of what gives us 16? That number must be 4. 2 to the power of 4 gives us 16. So this whole thing becomes 4. Copy paste this. Alright, so this is what it's supposed to be as a previous problem. We had 3 to the power of 4, which is 81. Oh, this is a different problem, actually. Different output, actually. So 3 to the power of 4 gives us 81, which would be equivalent to this argument. I hope this quadratic is good. Minus 81 from both sides. Equal to 0. So therefore factors of 2, 2, and 1. Factors of 81. 9 times 9. That's perfect. What do you know? Alright. So we have 2x with a 9, and then 1x with another 9. Both signs are different. And then the larger of the two is negative. So this is a large of the two. So that's negative. And the smaller of the two is positive. So thus we get two answers. We have x is equal to negative 9 over 2. And positive 9. Two answers, but don't get too excited as usual. Make sure you double check your answers for extraneous solutions. So move back up. Well, we could already see the negative answer is going to fail because that causes a negative input, which is a domain issue. So that is extraneous. So this is probably the good one. Plug it back in. Yes, it's good. 18 minus 9 is positive, so yes, this is the good answer. So therefore only one solution, x is equal to positive 9. And we are good to go. And that's it for today. A couple of scuffed problems. I think there were like 2 or 3 bad problems, but the other ones are good. And I think that pretty much does it for these type of log problems. Probably next time I'm going to cover the natural log, this one right here. Then also other types of log problems. You might see something like this. You might see, for example, 2 to the power of 3 is equal to 3 to the power of x. What happens when you can't match the bases very nicely? So this is base 2, this is base 3. This is already a prime number. This is also a prime number. So in this situation, what do you do? This calls for logs. But that's more for next time. But that basically concludes it for the day. It's just a short marathon of problems. And I'll probably see you in another time. You have a good one. And that's it.